Okay, here's a problem that covers buoyant forces. I'd like to put one like this on the exam because I think it's a pretty straightforward problem to understand, and you can use a free body diagram and the formula for buoyant forces and come up with some interesting kinds of problems like this one. Okay, so in this problem, we're trying to calculate the body fat percentage for an athlete. Okay, the athlete has a mass of 90 kilograms, and I put this comment in here, measured with a spring scale under normal atmospheric conditions. Okay, so he or she is not immersed in water. Okay, it's just in regular atmospheric conditions. All right, so I also mentioned that it's a spring scale because I think we all understand that a spring scale actually is measuring the force exerted against the scale. Okay, why is that important? Because in the next line it says the athlete has a measured mass of 5 kilograms when submersed in water. Well, we've talked about mass, the difference between mass and weight. The difference is that gravity is involved. All right, so here's this situation where I have this athlete that weighs 90 kilograms, but when the athlete's submerged, it would be 5 kilograms. Okay, so we know that the mass of the athlete doesn't really change. It's really the reading on the scale. Okay, so I have a bathroom scale. I can switch the mode over to kilograms and it will report back my weight in kilograms. It's actually a good measure of mass because they backed out the gravity. Okay, so that's what's going on here. That explains why this reading is 5 kilograms. The buoyant force is counteracting gravity. Okay, the other thing in this problem you need to consider is that if you're doing a body fat analysis, you have to worry about the air in your lungs. Okay, so let's assume that the athlete exhales and there's still 1.5 liters of air left in the lungs. Okay, so given all that, and the density of water is 1 gram per cubic centimeter, and that's, by the way, the same thing as 1,000 kilograms per cubic meter. Okay, so what we want to do here is determine the overall body density of the athlete, and the units we want to report in are grams per cubic centimeter. Okay, so let's get started with that. So step 1 is a free body diagram. So in this case, it's actually a body. All right, a free body diagram. So what are the forces that are working on the body? Okay, so we're assuming that in this particular case, the body's immersed in water. All right, so we know there's a weight force due to gravity, so I'll draw a W moving down. We also know what that value is. It's 90 kilograms times 9.8 meters per second squared. Okay, so we know that this unit, kilograms meters per second squared, is actually newtons. So this is the same thing as (90 times 9.8 newtons). Okay. All right, so we have that weight coming down, and then there's a reactive force at the scale. I'm going to call that R. All right, and so that's measured to be 5 kilograms, so 5 times 9.8, and that would be in newtons. And there's a buoyant force. All right, so we can tell from this diagram that the buoyant force acting up would be the difference between the weight and the reactive force. Okay, so in this case, that's going to be 90 minus 5, which is 85 times 9.8 newtons. Okay, so you'll notice I didn't actually multiply out the 9.8 because later on it's going to divide out, so I just left it there. Okay, so from there, we know the equation for buoyant force. It's going to be the density of the fluid that's displaced, in this case the density of water, okay, times gravity times the volume of the water that's displaced, which in this case would be the volume of the body, almost. Okay, I'm going to put a prime there because what we know is that the body also has air trapped in the lungs, and so we want to subtract off that particular volume to get the density calculation for the body. Okay, so here we are, we're ready to go. We know that this is 85 times 9.8 is equal to, all right, so we can put this in cubic meters. All right, so this would be 1,000 kilograms per cubic meter times gravity, 9.8 meters per second squared, times the volume of the body with the air in the lungs. Okay, so let's check our units. That's one thing that you should be in the habit of doing to make sure the units seem to work out. All right, so I see kilograms, meter, second squared. I know that part is newtons, so that makes me feel good. And then I know that volume is in meters cubed, and so that meters cubed would cancel here, and I'd be left with simply newtons. And so everything's dimensionally correct here. All right, so I can solve for the volume of the body, and I get 0.085 cubic meters. All right, so next I need to subtract off the volume that's held in the lungs. Okay, so I know that I have 1.5 liters in the lungs, and in 1 liter I have 1,000 milliliters. Okay, and then in 1 milliliter I have 1 cubic centimeter. Okay, so I've told you that's the link between liters and the length measurement in the metric system. I happen to remember that. That's why I needed to move this towards 1 milliliter equals 1 cubic centimeter. I went from liters to milliliters to cubic centimeters. Now I need to move back to meters. Okay, so I know I have in 100 centimeters, there's 1 meter. So if I cube everything, I would have that conversion between cubic centimeters and cubic meters. Okay, so that gives me the volume of the lungs. I can do that calculation and subtract from VP prime, and I get a slight adjustment. This is not a very big number, but I get a slight adjustment. I get the volume being, okay, I get the volume to be 0.0835 cubic meters. All right. So from there, it's pretty straightforward to get to the density. All right. So I take the mass of the athlete, 90 kilograms, and I divide by the volume. And I get a number of 1,777.8 kilograms per meter cubed. And you can do that conversion. It asks for this number in grams per cubic centimeter. So I can convert both those units to be 1.078. Okay, just carried one less significant digit. Grams per cubic centimeter. Okay, so a quick question might be, does the athlete float? And the density of water is 1 gram per cubic centimeter. This is heavier than water, and so in this case, this person would not float. All right, so that's the main part that I want you to know about. That's part A. All right, you had to do a little twist on the buoyant force kind of problem. I also wanted to talk about part B. I'm not so much caring about this being on the exam, but I wanted you to know how to think about this. We know that the overall density is 1.078 grams per cubic centimeter. Okay, so if we were wanting to find the body fat percentage, and we knew that fat is 0.9 grams per cubic centimeter, and that would occupy a certain percentage of the body, okay, we'll call that X. So X equals body fat. Okay, what's left? Well, X is a ratio, so if you wanted the total, it would be 1 minus X is equal to the lean mass. Okay, so X is going to be a number between 0 and 1, indicating what portion of the body is body fat. Okay, so that's the case, and we knew that the lean mass density is 1.1. We would then multiply that by 1 minus X. Okay, and again, this would be in grams per cubic centimeter. All right, so stripping out the units, we have this little equation here. If I solve for X, I get the body fat percentage. Okay, so when I do that, I get X equals 0.11, which implies that we have 11% body fat in this case. All right, you should know that there's other models, the 0.9 and 1.1, those vary from person to person, and so they've looked at different ways of estimating body fat. And so this particular formula is not the standard that you would use for body fat. There's other formulas. If you Google those, you can find them. But this does get you in the ballpark within 1% or 2%. Anyway, that's a Bouyant Force problem.